Now, we use them for energy. Does anybody know how much energy we get from carbohydrates? It's 4 calories per gram, and that's an important number when we compare that with the number on Monday that we'll be talking about. So 4 big C calories are actually kilocalories. 4 big C calories per gram. It is the body's preferred energy source. The pathway of cellular respiration is designed to utilize glucose in order to generate ATP. We can use other substances, but they have to be converted and kind of cycled into those pathways. It's designed to utilize glucose. Now, we don't just use carbohydrates for immediate energy, but also stored energy, right?
Yes.
Okay. What's another function of carbohydrates, although it does not apply to you and me as humans? Structure, that's right. We don't use carbohydrates for structure, but we are among the very few organisms that do not. Most organisms do. Why is it that you and I don't need carbohydrates for structure? Yeah, we've got bones, okay? So we don't need carbohydrates for structure. We don't have cell walls because we have our vertebrates. We have a skeleton. Now, when we think about carbohydrates, what elements are common to all carbohydrates? CHO, right? Remember CHO, carbon, hydrogen, and oxygen. We've got CHO. What other biomolecule group can be defined as CHO? Lipids, very good. So how do I distinguish, and you will have to do that on your exam, how do I distinguish between a carbohydrate and a lipid? That ratio, 2-to-1 ratio. 2 whats to 1 what? 2 hydrogens to 1 oxygen, and to which group does that ratio apply? Carbohydrates. And guys, you know this even if you haven't really connected it. You don't have to count oxygens when you're trying to determine if something's a lipid or a carbohydrate, because what do we know about lipids? What is their defining characteristic?
There's no fatty acid chain.
They've got those fatty acid chains. They're non-polar. They're hydrophobic. What element do we associate with polarity? What element?
Oxygen.
Oxygen, right? Oxygen. So if lipids are non-polar, what does that tell me? While they have oxygen, they hardly have any, or they would not be non-polar, right? So it's not like I have to count carbohydrates. There might be 16 oxygens. In the lipid, there might be 1. Okay? I mean, it's not even close.
So it's 2 oxygens to 1 hydrogen?
2 hydrogens to 1 oxygen in carbohydrates. Okay. So they contain CHO. Now, when we look at that carbohydrate formula, the way that we write the empirical formula is basically it's some type of multiple of CH2O, and that N is what that multiple is, how many carbons there are. Okay, so generally speaking, it's in multiple. We've got that 2-to-1 ratio, as you said. How many carbons there are? Right? So we have trioses, pentoses, hexoses, etc. And when we look at our carbohydrates, we can see that they form very large molecules made up of many repeating units, in other words, polymers. And if I've got a carbohydrate that is classified as a polymer, I can also identify that monomer, that building block. What is the monomer of our polysaccharides, our larger carbohydrates? A monosaccharide, right? Saccharide means sugar. We know our roots, so we understand the difference between them. Now, when we look at carbohydrates, there are functional groups that are common to all carbohydrates, and of course, we always want to make sure we know our functional groups. Taking a look at that carbohydrate, what functional groups do we see in carbohydrates? Lots of hydroxyls, right? There are lots of hydroxyl groups. And there is another functional group that's associated with carbohydrates. Carbonyl, very good. Okay, so we've got a carbonyl group and multiple hydroxyl groups, and that, of course, is the reason carbohydrates are so friendly with water. They're hydrophilic. So we're going to cover the carbohydrates that you're already familiar with. These are all carbohydrates that you have been exposed to before. First of all, we classify our monosaccharides based on the number of carbons, and you are familiar with these 2 pentoses, yes? Yeah, of course, we've heard of these guys before, and we'll be talking about them again. Why will we be talking about them again in our unit? Where do we see ribose? Nucleotides. Nucleotides specifically for RNA, right? So RNA nucleotides have ribose, whereas deoxyribose found in DNA nucleotides. What about ATP? Yeah, adenosine triphosphate. Which pentose does it have?
Right.
No.
Has ribose. ATP has ribose as its 5-carbon sugar, as its pentose. Now, when we look at, when we look at those pentoses, we see very clearly where the name deoxyribose comes from, right? How is deoxyribose different than ribose, as the roots would imply? There's one less oxygen, right? So we've got one less oxygen in deoxyribose as compared to ribose. Therefore, these are not true, what do we call molecules that I say your number, what's that? They're not isomers, right? They are not isomers, very good. Okay. All right, that is not true, however, for our hexoses. Our hexoses are isomers. They are, of course, 6-carbon sugars, all 3 of them having the formula C6H12O6. These, again, should look familiar to you. Those are our 3 hexoses. One of the things that I want to make sure that you are not confused by is the way that these sugars are written. Okay, first of all, in understanding the formula in its simplest sense, we oftentimes write it in linear form, but in actuality, these carbohydrates form ring structures in solution, in vivo, in a living thing. It's beyond the scope of this class to understand how that happens, but just to recognize that it does happen. Now notice how our simple sugars are classified. These words should look familiar to you. If not familiar, they should be decipherable by you, right? What will we predict about a sugar that we call an aldose? What will we predict about its carbonyl group? It's an aldehyde, whereas of course our ketoses, those carbonyl groups are ketones, right? And so that makes sense to us. So we've already talked about glucose, okay? Glucose found in honey, preferred energy source for our cells. Fructose, where do we find fructose, as the name would imply? In fruit. This is a very sweet monosaccharide. Fructose is the sweetest of the 3. And of course, galactose, we're familiar with that as a monomer of, yeah, milk sugar, lactose. Very good. All right, let's skip that. So disaccharides. If I have 2 monosaccharides and I join them together, obviously I'm going to make a disaccharide. What reaction occurs to join those monomers together? Dehydration synthesis. And that was the problem with some of the formulas you gave me on your pop quiz for the bonus question. Because if I am making a disaccharide from 2 hexoses, let's brainstorm what would that formula, or what would that formula be? First of all, how many carbons am I going to have if I add a C6H12 to a C6H12? 12. I'm going to have 12. Okay, so all of my disaccharides have 12 carbons. What about the number of hydrogens? 22. Very good. Where did he get 22? Can't add 12 and 12, right?
You're going to take 2 hydrogens.
Yes, exactly. So we've got 22 hydrogens and how many oxygens? 11, because my H2O has an O also, right? So in order to form my disaccharide, I'm going to lose a molecule of water in order to generate that. And what type of bond is forming between those 2 monosaccharides to form that disaccharide? A covalent bond. Now remember, we're talking about amino acids. What did we say is the name of that covalent bond that we use to join together amino acids? Peptide bond. Remember I told you that each group has a different name for its, yeah. So with carbohydrates, we call it a glycosidic linkage. I know, just to drive you guys crazy. What can I say? Throw around a lot of big words, everybody assumes you're brilliant, yes? There you go. Glycosidic. Glycosidic linkage. Yeah.
And that's just the name of
Between monosaccharides. Yeah. Okay. All right, guys. So let's take a look at these disaccharides. They should look familiar to you. Yes. Yes. Learned these before. You do need to know the monomers for them. And as you recall, I hope each of them, sucrose, lactose, and maltose, one of those monomers is glucose. So it's only then figuring out what is that second one. So sucrose, what's the common name for sucrose? Table sugar. Is table sugar sweet?
Yes.
Oh yeah. So besides glucose, what did we just say was the very sweet fructose? So sucrose is glu plus fruit. What about lactose? Where do we find that? In milk. That is milk sugar. It is glu plus the lact. Now, of course, we know that some people are lactose intolerant. How many of you are lactose intolerant? It used to be that all adults were lactose intolerant. We stopped making the enzyme lactase as adults because years ago, people didn't drink milk as adults. I mean, that virtually meant you were still nursing, and at some age, you gotta give that up, right? You keep doing that. So people did not drink milk as adults. They lost the ability to metabolize lactose. Now we see there are certain segments of the population that maintain that ability to produce lactase. So what does it mean if I don't make lactase, which I personally do not? I am lactose intolerant. What does that mean? It means that if I drink a glass of milk, that lactose sits in my gut. I don't have the ability to break down that disaccharide into monosaccharides. Therefore, I can't absorb any nutritional value from that milk. There's nothing I can do with it. Why is that important? Because it means that the bacteria in my gut are like, woohoo, she's drinking milk again, lactose. And so the bacteria start to metabolize it. As they metabolize it, they produce as a waste product gas. And so you end up feeling bloated and kind of crampy and yucky as a result of that. You've just given your bacteria more food than normal because they are metabolizing the lactose. Okay, now maltose, what's the only combination left for maltose? Glu plus glue. Okay, maltose is a non-sweet sugar. We associate maltose with seeds, malt liquor. It's used for brewing. If you've ever heard, I'm sure not experienced, malt liquor. Okay, so it is found in seeds, the disaccharide. So let's take a look at these illustrations of disaccharides, and I will tell you that you tell me, would it be fair for me to put this on an exam and ask you to identify that disaccharide?
No.
Yes. Wait, oh no whining. What the heck? Guys, that is a very fair question. I want you to look at this disaccharide and tell me why that is fair based on what we've already talked about.
Oh, it's maltose.
How do you know that?
It's the same thing.
See? All right. So guys, notice the monomers of this disaccharide are identical. What is the only disaccharide in which the monomers are identical?
Maltose.
Maltose. So my point is, if you get to something on an exam or in a lab and you're like, oh my gosh, she's really gone crazy. How would you expect us to know that? Look again. I may have gone crazy, but still, there's a good reason I put it on there. You just need to think a little harder. You have the tools to answer it, okay? So that would be maltose. Would I expect you to know the second one? No, okay? It could be one of two possibilities. What could it be? Could be sucrose, it could be lactose. It happens to be sucrose, but I wouldn't expect you to know that one, okay? Any questions on that? Alrighty, so let's talk about polysaccharides. How do I make a polysaccharide? I join together lots of monosaccharides every time through what reaction? Dehydration synthesis, every time losing a molecule of water. So if I join together 523 monosaccharides, how many molecules of water did I lose? 522, that's right, because to join the first two together, I only lose one molecule of water, right? And then all the rest I add, I lose another molecule of water. Good job, guys.
Wait, I'm still confused.
What?
Why is it one less than how many?
Because for the first two, I only lose one water molecule, right?
And then,
So to join together two sugars, I've lost one water.
okay, and then the
For each
two-
additional one is another water, but I'm gonna be one less every time,
Oh,
okay? All right, so guys. All right, so let's talk about our polysaccharides. We break them down into two